problems into your application which can be hard to replicate and fix. And that's all for the introduction. In the next module, hey, how you doing? I'm Elton, and this is what happens when the garbage collector runs, the next module in IDisposable Best Practices for C# developers here on Pluralsight. In this module, we're going to get a better understanding of what the garbage collector does, what happens when the garbage collector finds objects which aren't in use, and how using IDisposable correctly means our code works efficiently without relying on the garbage collector to do our cleanup for us. We'll also cover the best practice implementation of IDisposable, which allows you to build a class hierarchy where derived classes use different mixtures of managed and unmanaged resources, but they all get cleaned up correctly by following a simple pattern. A garbage collector is a component of a software runtime which takes care of the memory your app uses. More correctly, it manages the allocation and release of memory. Let's find out how that looks in practice. When you run a .NET application, the runtime creates an app domain, which is an isolated environment for that application. Each app domain can use memory in the stack and in the heap. Whenever you create an instance of a class in your code, a portion of memory is reserved for that object. That's virtual memory, which the operating system makes available to .NET, and it may be space in the physical RAM on the box, or in the swap space on disk if the OS is moving things around. That memory allocation for the object holds its state, the current values of any member variables, and its behavior, the methods that you can call on the object. The memory allocation is exclusively for that object, so no other object in that program, or any other .NET program, or any other program from another language can use that piece of memory until it's deallocated. Deallocating the memory happens in two ways. Firstly, when the program ends, all the address space that the operating system reserved for it becomes free again. So when your app exits, gracefully or because of a crash, all the memory that it had reserved gets deallocated. It doesn't matter how many objects are live or whether they've been disposed or finalized, the address space the OS gave to the .NET runtime for this instance of your app is reclaimed. So no matter how inefficient your app is or what state it's in, when it ends it won't hang on to any memory. The second way memory is deallocated happens while the app is running, and it's done by the garbage collector. The garbage collector looks at every piece of memory the app has allocated and checks to see if the object using that memory is still reachable by the code. In the case of local variables which were used in a method and are no longer accessible, they'll be flagged as dead. But any objects which are reachable, like an instance field being used in the entry point to your app, that's flagged as still alive. After it's checked all the objects in the memory used by the app, the GC deallocates all the memory used by dead objects, so that memory becomes available again, and it compresses the heap so available memory can be used more efficiently. Now actually that's a simplified version of what the GC does, and in the next clip we'll go down to another level of detail, because to write efficient .NET apps, this is something that you need to understand. Running a garbage collection is expensive because it requires the GC to walk the whole object graph in your app and check every object's usage to see if there are any live references to it. So the .NET garbage collector uses a more complex mechanism to make sure it runs efficiently. The GC groups objects into different generations. The basic assumption is that old objects, those which have already survived a previous collection, are long-lived and they don't need to be checked every time the GC runs. Whereas objects that haven't been seen by the GC before are new and they could be short-lived, so they do get checked every time. The .NET GC has three collections, Gen 0, Gen 1 and Gen 2. If an object survives Gen 0 collection because it's still being referenced in the app, it gets moved to Gen 1, which is collected less frequently. If it's not being referenced, it gets flagged for removal. Next time the GC runs, there will be new objects in Gen 0 to check, and again, if they're still in use, they'll be moved to Gen 1, and if not, they'll be flagged for removal. But now the Gen 1 objects are also checked, and if they're still in use, they'll survive Gen 1 collection and get moved to Gen 2. Otherwise, they get flagged for removal. So during the typical running of your application, you'll have lots of objects that come in and out of Gen 0, some objects in Gen 1, and a few long-lived objects in Gen 2. And the GC only does a full collection, checking all objects in all generations when the app is running low on available memory. And there's still more that the .NET garbage collector does. It actually manages two memory heaps, the standard heap used for most objects, and an additional heap used specifically for large objects that take up a lot of memory. When the GC runs, it can check both heaps for dead objects and flag them for cleanup. When it has deallocated dead objects after a collection, it compresses the ordinary heap, removing gaps to make the remaining memory available in one block, which makes allocating memory for new objects more efficient than trying to allocate across many small pieces of available memory. The large object heap doesn't get compressed automatically, so the GC doesn't spend time moving bigger chunks of memory around. So when the garbage collector runs, it does a lot of work. And the main job of the GC is to get a balance between keeping memory available for the app to use, ideally contiguous memory so allocation is faster, but also not slowing down the application and soaking up processor time. It does that by running collections efficiently and by running them infrequently. So in principle, that's what the GC does. I've simplified some of the details, and I'll go on to describe where IDisposable comes in during the module, but in brief we've seen what happens when the GC collects. But when does the GC actually run a collection? Well, there are different trigger points for different types of collection. When you allocate a new object in code, before the allocation happens, the GC checks to see how much memory the app is using. If the GC doesn't like the amount of memory the app has still available, it considers the app to be under memory pressure and it will trigger a collection. Whether it's a full collection or a partial collection depends on how much pressure the app is under. The GC has thresholds to decide if it can run a quick Gen 0 collection, or both Gen 0 and Gen 1, or if it needs to run a full, expensive Generation 2 collection. When the GC decides that it needs to run a collection, it kicks it off in the background. There are variations of this that you can configure, but generally the GC runs its collection in a separate thread while the rest of your app carries on running in the main thread. If the collection has been triggered by your app allocating some memory for a new object, your allocation will happen and the work will carry on running on the main thread while the GC is checking allocated objects for liveness in the background thread. So the GC tries not to impact your running application, but it still needs to use compute resources for every run, so it aims to run as infrequently and as efficiently as possible, which is where you can help by correctly using IDisposable. That's enough theory for the moment, so next we'll have a look at what actually happens when the GC runs. I've got a demo coming up where we'll go back to using the SQL connection class, and I've put that getDate code from the module introducing IDisposable into a console app that we can monitor as we're running. In this first demo, I'll be using static variables in my program class and I won't dispose anything. I'll run the app in debug mode with Visual Studio's memory profiler, which we can use to collect statistics about allocated objects and memory so we can profile the app at different times. And then I'll force the garbage collector to run and see what happens with our object graph after collection. If you want to follow along with the demos for this module, you just need to have a local SQL Server instance running, and I'm using a Docker container for that with an image that I've already packaged up and put on Docker Hub. So the easiest way to follow along is to pick up the README file in the downloads and run this Docker command. Now I've already got Docker running, so if I open my terminal, I'll just make sure my database is still there and my container is there. It's listing on port 1433, which is the default SQL Server port. So now I'll switch over to the full Visual Studio and we'll have a look at this SQL consumer solution. So here's the code for that database state class. It does the same thing that we've seen in other modules. It opens up a SQL connection, and when you call this getDate method, it just executes a SQL command and returns the value of the current date from the database. The SQL command is a disposable object, and that gets used inside a using block. But the SQL connection object is a local field, and that doesn't get disposed. So there's one big implementation difference with this version of the class. I'm not implementing IDisposable, so I'm going to have issues when I run it. In the program class, for this first iteration, I have a static field for an instance of the database state class. When the application runs, it loads the configuration settings from JSON using the standard .NET configuration libraries. It prints out some instructions, and when the user hits G, it runs this getDate method. In the getDate method, that static database state field gets instantiated if it hasn't been created already, and then we make a call to the getDate method and print out the results to the console. So the first thing I'll do is I'll start my app in debug mode, and then I'm going to go back to Visual Studio and I'm going to go to the debug menu and open the window for the diagnostic tools. There are lots of ways to profile .NET applications, but this view is built right into all versions of Visual Studio, including the free Community Edition. It's super easy to use and it gives you all the details you need. My app's running and currently it's not doing anything, but I'll take a snapshot of memory right now. But we won't analyze it just yet, and I'm going to hide the details that Visual Studio is showing me. So first I'm going to get the app to do something. So I'll hit G, which instantiates my database state instance, calls getDate using a SQL command and a SQL connection, and it doesn't dispose of them. So my call has worked, and I'll take another snapshot now. And I'll hide those details just for a second. We've had one run of the method. We know we'll have an instance of the database state class, which has its own instance of the SQL connection class, and they'll both be live because the app can still use them. The program class is still active, and that database state object is a static field, so it still has a live reference. We'll have more than 2 live objects in the heap though, because I have a console that .NET has drawn, there's some framework code to write to the console and to read the configuration from JSON. So how many live objects do you think we'll have? 10? 100? Let's see. Actually, it's over 3,000, which sounds like a huge amount, and it is. We've only allocated a few hundred kilobytes of memory in the heap, but we have lots of objects in there. If I follow the link here, I can see all the classes that have instances, and it's sorted by the number of objects, and I have over 1,000 strings here. I can drill down into the instances and see that a lot of these strings are static variables, and if I scroll down I'll see more static variables to do with the SQL client classes. So I can guess that these are optimizations in .NET, which mean loading and reading configuration and making SQL calls puts a whole load of strings into memory. Up here I can filter by type names, so I'll search for my own SQL consumer namespace, and I'll see just one object there, which is my database state object. It's using a tiny amount of memory by itself, just 32 bytes, but the inclusive size here includes all the child objects, and that's more like 13 kilobytes. The paths to root here shows me how the object is still alive, and if I open this up, we can see that static field reference inside my program class, and if I look at the reference types, it will show me the objects that this object still owns. So I've got my SQL connection in there, and inside there I can see an internal connection and my database pool and some strings in there. So I've really only executed one line of code that I care about, and we can see there's already lots of objects that the garbage collector is going to need to manage. And next we'll go back to that program class and we'll change it to use a local variable instead of a static field and see how that compares. In this clip, I'll continue with the same demo application, but I'll change from using a static field to using local variables. I still won't dispose any objects and will use profiling to check for object leaks. That's where memory consumption keeps increasing because we've got unused objects that the garbage collector won't clean up. So my app is still running here, and if we compare our snapshot with the 3000 allocations to the very first snapshot, which was taken after the app had written to the console, but before we did anything, there were originally 570 objects using about 150 kilobytes of memory. So running our code once has allocated another 2700 objects and around 250k of memory. But that's not necessarily an issue unless it does that every time we run the method. Let's check. So if I go back to my application here, and I'll run the getDate method another 10 times. Now I'll take another object snapshot, and we can see there's a little bit of variation there. There's 57 new objects and 4 more kilobytes of memory, but we still have around 3000 objects and 400 odd kilobytes, so we don't have a big object leak in our code. If I go back to the app and force a garbage collection, now that runs this code in the programmed class. That does a full Generation 2 garbage collection, so it's the most expensive and most thorough collection, and the app has waited until the collection is complete. Now I'll take another snapshot. The process memory graph here shows me that the garbage collection has happened, that's with that little yellow marker, but the results are much the same, 3000 odd objects, 400 kilobytes of memory. So we can expect that all of those 3000 objects are still live, and so they're not being collected. Now let's see what happens if I use a local variable instead of the static field. So I'll comment out this code here, and I'll create a new variable, using the same configuration that I've already loaded, and in my console line I'll call getDate on that new local variable. So as soon as this method's completed, my variable s is going to grow out of scope, so it should be viable for the garbage collector to clean that up for me. Now remember, my database state class in this version doesn't implement IDisposable, so my best practice number 1, dispose of disposable objects as soon as possible, doesn't apply here. So I'll debug that code again, and I'll open the diagnostic tools with Ctrl-Alt-F2. And one important thing here is that these diagnostic tools only work in debug mode in Visual Studio. But if you're doing more detailed analysis on your app, then you should build it and profile it in release mode. In debug mode, there are some differences in how .NET references live objects, so the instance counts that we see won't be quite correct, but they'll be fine for making a comparison. So let's see if my change has made a difference. I'll take a snapshot now, and I'll go back to my app and run getDate once, and then I'll take another snapshot. And this looks very similar to the original application. The first snapshot has about 150k and 570 objects. By the second snapshot, we've allocated 2,700 more objects and another 250k of memory, so the profile is very similar. I'll go back to my app and I'll run getDate another 10 times. And we can see back in the profile that the memory graph is creeping up. It's only a small increase, but there is an upward trend. And if I check that by taking another snapshot now, I now have over 4,000 objects, so this is definitely a problem. My memory usage is only creeping up a small amount, but this is a tiny piece of code. If I were doing a lot more work and running in a tight loop, I could soon be using hundreds of megabytes, and once allocated they wouldn't be quickly released. Looking at the objects in use here, I have 1,000 odd strings, which isn't very different from the original version, but there's a SQL connection timeout object high up in the list here, with around 70 instances, and there are the same number of instances of the stopwatch class, which suggests that those two have been created together every time I create a SQL connection, and they're not being cleaned up. If I go back to my app again and force that level 2 garbage collection, and back in the diagnostic tools, I can see the collections happened, and I take another snapshot. The number of objects doesn't really change. Certainly it doesn't go back to the baseline of 3,000 objects, so this code is doing pretty badly at cleaning up. And next we'll talk about what's actually happening when we run this code. Now we've seen the garbage collector in practice, and we've looked at what happens when IDisposable objects are not used correctly. In the first run of the code, our console app allocated a single database state instance as a static field, which in turn instantiated a single SQL connection instance for talking to SQL Server. Nothing gets disposed. When we ran the app and took some snapshots with the memory profiler, just running the console without doing any work allocated around 500 objects, mostly in the system namespace, and they're objects .NET uses to manage the app domain and the console. When we ran a call to get data from SQL Server, the object count leapt up to 3,000, and again most of those were in the system namespace. There's strings and other objects used by the data and configuration libraries. Calling getDate multiple times in the console didn't appreciably change the number of objects allocated, as we're reusing the same objects to make that database call. And when we forced a garbage collection, the object count stayed the same because all those objects can be referenced by the running app, so the whole object graph is still live and there's nothing to be cleaned up. In the second version of the app, we use a new database state instance every time the user ran getDate from the console, but we didn't follow the IDisposable best practices. The database state instance uses a SQL connection, but doesn't dispose it. So each time we run, there's a stack of objects from the database state instance and all the allocations that it made in the call tree, which aren't being cleaned up as soon as we finish with them. When we ran this version of the app, we got the same 500 odd object allocations, and when we ran getDate, that jumped to 3,000. When we ran getDate repeatedly, the object count kept increasing, adding a few hundred objects every time we made the call. Quickly we had 4,500 objects allocated, and although most of those were local variables which had gone out of scope, the garbage collector didn't clean them up. That's because there was no trigger to run a collection. The app wasn't under memory pressure next time we allocated a bunch of objects, so the GC didn't need to run. When we forced the GC to run, the objects in the graph for those unused database state instances didn't get cleaned up, but that's because we were running in a debug build where objects get tracked slightly differently. In a release build, we would expect those unreferenced objects to get collected, but only when the garbage collector decided the app was under memory pressure. Then we will be back to the baseline. Those won't ever get cleared up because .NET is deliberately keeping them in memory for optimization. So in the second version of our console application, after running for a while, we had this scenario with 3,000 objects that .NET wants to keep in memory and 1,000 objects from our getDate calls which we're not using anymore. This app was running with a minimal memory footprint, so there's no immediate need for the GC to run and clean up those 1,000 unused objects. How much memory your app can use depends upon your hardware and operating system. Compiled for 32-bit, you could theoretically access 2 GB of memory, and for 64-bit the limit is practically all the memory in your server. The GC has thresholds to decide when to run a collection. Those thresholds get adjusted as the app is running and the GC learns more about its behavior, but the defaults range from 16 MB of memory allocated for 32-bit processes up to 4 GB for 64-bit processes. If this was a long-running app, and assuming that it could keep running without exhausting the SQL connection pool, then we could easily get to hundreds of thousands of objects allocated before the GC ran. That's hundreds of thousands of objects that the GC needs to check for liveness, and it could need to clean up and compact hundreds of megabytes. And again, it doesn't sound like a big deal when you're running on a server with gigabytes of RAM, but .NET apps running in Linux containers are using a really lightweight environment, and they might only have a few hundred megabytes of memory made available to them. But even so, the garbage collector is built to be fast and efficient, so even with lots of work to do, you may not see much performance impact in your app, but leaving the GC to work out that objects aren't being used at the point when your app is under pressure is just unnecessary, when you know in your code that you finished using the object yourself and you could free up the resources immediately, saving the GC a lot of work. And we know that we should clean up disposable objects as soon as we can, but our database state class currently doesn't implement IDisposable, so we can't. And in the next demo, we're going to go on and fix that. In this demo, we're going to implement IDisposable on the database state class, so consumers of it, like our console application, can clean up resources as soon as they're not needed, rather than waiting for the GC to do it for them. We'll follow the standard pattern for implementing IDisposable in a class which could be extended to allow for subclasses to join in disposing their own IDisposable members, and also to dispose of any unmanaged resources that they may have. So back in Visual Studio, if I add the IDisposable interface to my class, and I let Visual Studio generate a stub implementation, I get a couple of options here. If I choose to use the dispose pattern, I'm going to get this whole big chunk of code with all the best practices that you're going to learn about in this module. So that's the option that you should really choose, but I'm going to start with the basic interface implementation and then build up to the dispose pattern so you can see why it's useful. So I have a public dispose method here, and I could do my disposing in there and clean up the SQL connection, but that's not a good idea. What I should do is add a second dispose method, protected this time, and virtual so that it can be overridden. And this takes a Boolean flag saying whether or not the object is being disposed. Then in the public method, I'm going to call the protected method, passing it the value true, so we know that we're in a dispose call. And then on the garbage collector, I'm going to call suppress finalize to let the garbage collector know that this instance has cleaned up all of its own resources and that it doesn't need to be finalized. We'll look at finalizers shortly, but for now we just need to know that finalizers are expensive, and this line of code saves us that expensive call, which we don't need because we'll have done our own cleanup. In the protected dispose method, I'm going to check the disposing flag. The flag is there to help me work out what I need to dispose if I've got managed and unmanaged resources. So in this case, if I'm in a disposing call, I need to check if my SQL connection object is not null, and if it isn't, then I call dispose on that object, and then set that object to be null. Your dispose code shouldn't throw any exceptions, and you should allow consumers to call dispose multiple times without any failures. If I had a lot to do in my dispose method, I could maintain a private Boolean field telling me whether this instance has been disposed. And then I'll check that flag in the dispose call. So I only do the disposal if dispose hasn't already been called, and when I have dispose, I'll set the flag. This flag is also a useful thing to have to protect against someone really misusing your class. The .NET guidelines say an object which has been disposed should throw an object disposed exception if consumers try to access any members. So in the getDate method here, I can check that disposed flag, and if it's been set, then I can throw an object disposed exception. Although this is good practice, it's far more common to see objects not disposed correctly rather than objects disposed and then used again. So you don't typically need to do this unless someone using your class after it's been disposed is going to cause unwanted behavior. Now we have a correct implementation of IDisposable, and in the next clip we'll see what happens with our object profiling when we start disposing of our objects correctly. In this demo, we'll continue with our new IDisposable implementation. We'll use a local variable in our console app, but we'll dispose of it as soon as we've used it, and see how our memory profile looks, and look at the number of objects that the GC needs to manage. So now that my database state object implements IDisposable back in the program class, I can replace my straight object initializer with a using block. And now we can start using our best practices for IDisposable and not relying on some future garbage collection run to clean up objects which I know that I'm not using. Implementing and using IDisposable was pretty easy, even taking the time to implement it correctly. Now I'll run that revised app in debug mode again with the profiler, and we'll see what a difference that change has made. So the same procedure as before, I'll open the diagnostic tools and take the initial snapshot before we do any work. Then I'll run getDate once, take another snapshot, and now we're up to that 3,000 odd objects, which looks like it's being the baseline state for our application once it's warmed up. So now I'll run getDate another 10 times, and now I'll take another snapshot. So we have a couple more K allocated in the heap, and the object count has gone up a small amount, but this is much better than the 800 plus new objects that we had when we weren't disposing of our local variables. So if I repeat that just to be sure, I'll run getDate another 10 times, and take another snapshot, and here we can see the difference. With the previous code where the object wasn't disposing of the SQL connection, but the GC hadn't run because the app still had plenty of memory available, we would have had 4,000 or 5,000 objects by now. With the new code, I still have the same 3,000 odd objects, and if I look at the latest snapshot, and I search for my namespace, we can see there are no objects there. So I have none of my own objects still live, which means they've been cleared up, and any objects they had allocated have also been cleared up, without me having to wait for the GC to run. If I clear the filter, then I'll see those SQL connection and stopwatch objects aren't there anymore, and although there are still thousands of objects, these are the things which .NET is deliberately keeping alive to optimize performance, not objects which my own code has explicitly used and failed to clean up. If I go back to the app now, force a garbage collection, and then take another snapshot, the memory profile hasn't really changed because there was no big allocation of unused objects just waiting to be collected. In ordinary usage, when the GC does run, it will have a lot less to do, 3,000 objects to check instead of 5,000, so it will run more quickly, which is good for the baseline speed of our application. And because we're disposing of the SQL connection when we've finished using it, the connection returns to the pool as soon as we're done, so that's good for the potential to scale our application. Next, we'll talk about those changes that we've made and some more best practices for your own applications. Our SQL consumer application is running a lot more smoothly now. We're using one instance of the database state class each time the user gets the date, and the class implements IDisposable, so we can follow the first best practice and dispose of instances as soon as we're finished with them. In the implementation of dispose, the database class first checks that it hasn't already been disposed, and then it disposes of the SQL connection instance, which closes the connection, returns it to the pool, cleans up the unmanaged resources, and basically frees up the stack of objects in that allocation tree. This means our app doesn't have any lurking issues with starving the connection pool, and we're not building up a huge amount of work for the garbage collector. We're taking ownership of cleanup ourselves so we can do it as soon as possible, which is the second best practice. If you write a class which has IDisposable objects as instance fields, implement IDisposable in that class, and when your object is disposing, call dispose on those instance fields. My database state class has a SQL connection as an instance field. SQL connection implements IDisposable, so I need to implement IDisposable as well. This is the standard dispose pattern, which we'll look at more closely in the next demo. But when my object is disposing, I call dispose on any live disposable fields, in this case the SQL connection object. I'm also being very careful in my dispose implementation to make sure that this method is safe. You shouldn't assume that dispose will only be called once on an object, so you need to check that any objects you do dispose are still in a valid state to be used, which is the third best practice. Allow dispose to be called multiple times and don't throw exceptions when you are disposing. Now actually these three are the most important practices, so if you follow them then your code will be in pretty good shape. But the protected dispose method and the GC suppress finalize call are both there for good reasons, so we should look at what they're doing before we finish with the garbage collector. When the GC runs and finds an object that isn't referenced, it cleans it up. But the GC doesn't know or care about IDisposable, so the .NET runtime doesn't call dispose for you. IDisposable is there for the user of the class to explicitly run the cleanup when an object's no longer in use. In the original demo app for this module, the database state class used a SQL connection instance and never called dispose, but we know you need to call dispose to close the connection and return it to the pool. So if we didn't ever call dispose and the GC doesn't call dispose, what happens to the open connections when the GC runs and cleans up the unreferenced database state objects and their SQL connection objects? In .NET, we have finalizers for this exact scenario. When a class is using unmanaged resources and it implements IDisposable, it should also define a finalizer, which will clean up only the unmanaged resources in case the consumer of the class doesn't call dispose. When the GC sees a finalizer defined on a class and it hasn't been told not to finalize that instance, it will run the finalizer. The finalizer is the last chance for unmanaged resources to be safely cleaned up. But having a finalizer on a class means it gets treated differently by the garbage collector, and objects with finalizers can live a lot longer in memory. So you only need a finalizer for classes that are using unmanaged objects. And next we'll have a demo to see how that works. In this demo, we're going to use a class which derives from our database state class and uses some additional resources of its own which need to be cleaned up. We'll implement a finalizer to deal with these unmanaged objects, and we'll do our cleanup in the protected dispose method, so we retain the disposing logic from the parent class. We'll see how this pattern works with the memory profiler to look at object allocations. So here's a subclass of database state called unmanaged database state. It has two member fields which we need to do something with: a SQL command object which implements IDisposable, and an int pointer which is a pointer to memory, and that's an unmanaged resource. I've made the getDate method in the base class virtual and overridden it in this class. I'm not actually adding anything here, but just to demonstrate, when the method gets called, I allocate the SQL command object by getting a command from the connection, which I know has been allocated in the base class by this point. And then I allocate the pointer using the allocHglobal method on the Marshall class, which is how I reserve a chunk of unmanaged memory and get a pointer to it. That might be something I need to do to interrupt with some unmanaged code, but here I'm just initializing and using that block of memory. My base class implements IDisposable, which means consumers can use instances of unmanaged database state disposable objects too, but if they call dispose, then they'll call the public method of the base class, which only disposes of the SQL connection and not the other resources that my unmanaged database state class is using. To do that, we'll go back to the derived class, and we'll override the virtual dispose method from the base class. That lets me add code to dispose of my own local object, so in this case my SQL command object. So if we're disposing, and my SQL command object is not null, then we dispose of it, and set it to null so we know that it's been dealt with. And we'll move this call to dispose on the base class after this one. So the base class method will run and clean up the other resources. But inside here, I also need to deal with my unmanaged resource. I need to clean that up whether I'm disposing or not. So I'll check if the pointer has been allocated. And if not, then I need to run another marshal call to free that block of memory. And that's the memory referenced by my pointer. And then I can set the pointer to 0 so that I know it's been dealt with. And this is where the disposing flag comes in. If a consumer forgets to call dispose on this class, the SQL objects won't be cleaned up until the garbage collector fires, but the unmanaged memory that we've allocated won't be freed up at all. The GC can't release it as it's just a pointer object and it doesn't know what it needs to do to clean it up. In the next clip, we'll add the code that we need for the GC to clean up this unmanaged resource using a finalizer. In this demo, we'll finish up our look at finalizers with unmanaged object cleanup. We'll see how to implement a finalizer and how that works with the dispose method to ensure that all our objects get cleaned up without writing duplicated code. We'll run the profiler for the last time to see that everything's cleaned up the way we expect. This unmanaged database state class does need a finalizer to deal with the unmanaged memory. In C#, finalizers are defined with a tilde and then the class name. So this is the finalizer for my class, which will run once for each object when it gets cleaned up by the GC, and not if they've already been disposed, as we're calling GC suppress finalize in the base class when we're disposing. So here I'm going to use the existing dispose method, but pass false so that only the unmanaged objects get cleaned up. That's important because I want to have one set of cleanup code in my dispose method, but it needs to do different things in different circumstances. When the object is being disposed, that means the consumer is finished with it and we're not running as part of a GC collection. All the objects used by this instance are still accessible, so we can call dispose on the SQL command, and then we can clean up the pointer. But if this method gets called as part of the finalizer, then the consumer hasn't called dispose. We're running in a GC collection and the GC has called finalize. At this point, the managed objects may have already been dealt with, so we can't necessarily access them. So we skip the managed resources, letting the GC deal with the SQL command, and we only clean up the pointer because the GC isn't going to do that for us. So now I'll go back to my program class and use the unmanaged database state object rather than the base class, and run my app again under the profiler. Like before, I'll take a snapshot now the application is loaded. Then I'll call getDate and take another snapshot. And getDate 10 more times. And take one more snapshot. Every call to the getDate method uses an instance of the new class in a using statement so that they all get disposed. And if I check the snapshot after making all those calls, there are still around 3,000 objects, so we're about the normal baseline for this application. We can see the memory in the graph isn't spiking. We don't see the 100 megabytes that the new objects allocate because that's unmanaged memory. The managed memory that my app uses on the heap still doesn't go above about 400k. If I go back to the app and force a collection, take a snapshot now, and the profile is still much the same. So our disposable implementation dealing with inheritance and unmanaged resources is still working nicely in our app, and there are no problems waiting to emerge. And next we'll recap what we've seen here and talk about what's coming in the next module. In that demo, we worked through an implementation of IDisposable which follows best practices in an inheritance hierarchy. Our derived class contained an additional disposable object as an instance field and an unmanaged resource, a pointer to a block of unmanaged memory. When instances of this class are disposing, we need to clean up those resources. We override the protected dispose method from the base class, the one with the disposing flag, and we leave the public dispose method unchanged. In the child class, when the object is being disposed, we dispose of the SQL command object if it's been initialized, and whether we're disposing or not, we're going to clean up the unmanaged resources. In this case, we do that with a marshal call to free the memory that we've allocated, and set the pointer so that we know we've done the cleanup. This is also where you would finish up any interop work that you've done with unmanaged resources, and then call dispose on the base class, passing the disposing flag, so the disposal continues through the whole hierarchy. In case consumers of this class haven't watched this course and don't call dispose, we need a way to clean up that unmanaged memory, which we do by having a finalizer on the class. If a class has a finalizer defined, the garbage collector creates a reference to the object when it's collecting an instance, so it knows there's a finalizer to call. That prolongs the life of the object, but it means we will always be able to clean up unmanaged resources. So in our finalizer, we call dispose, passing false, so we use the same disposing logic, but we only clean up the managed resources. At this point in the object's lifecycle, we can't be sure that any managed resources that it references still exist. They may have already been cleaned up, so we only want to work with the unmanaged resources. And that's a full implementation of the dispose pattern, which has given us a couple more best practices. Best practice number 4, if you implement IDisposable in a class which can be inherited, do your disposal logic in a protected virtual method, which child classes can override with their own cleanup logic. By following this, you ensure that each class in the hierarchy cleans up only its own resources. Derived classes clean up any fields that they define and call dispose on the base class for it to clean up its own fields. So every class is responsible for its own cleanup, and you don't risk having objects which are only partly cleaned up because they override the base class dispose method but don't call the base class to do its disposal. And the last one for this module, best practice number 5, only define a finalizer on your class if you are using unmanaged resources, and only release unmanaged resources in the finalizer. The finalizer should call the protected dispose method passing false, so that method ignores any managed resources and only releases unmanaged fields. This pattern means if consumers do use your class correctly and dispose of instances when they finish with them, the managed and unmanaged resources will be cleaned up straight away. If consumers don't call dispose, then if the object is out of scope, the next time the GC runs a collection, the GC will take care of cleaning up the managed resources, and your finalizer will run eventually to clean up the unmanaged resources. So that's what happens when the garbage collector runs, and how IDisposable fits in. We started off looking at the garbage collector's role, which is to ensure your app has sufficient memory available to keep running, and how that can be a costly operation in terms of processing, so the GC only runs a collection when it's needed. So if your app is using disposable objects but not disposing them, they will sit around taking up memory until the GC finds the app is under memory pressure and runs a collection to clean them up. We demonstrated how that works with a very simple app that we ran with the Visual Studio Profiler. Our app used the .NET configuration system to get a database connection string from config, and then made a call to get date on a configured SQL Server database. When we ran our app, we saw it was allocating about 3,000 objects to run that method. Without disposing the objects we used, that memory usage went up and up, causing the app to use more and more memory, and meaning the GC would have more and more work to do when it did run. By simply following the best practice from Module 1 and disposing the object as soon as we had used it, we kept the memory profile of our application flat. And we saw how to implement IDisposable correctly, calling dispose on any managed resources that are disposable, allowing dispose to be called multiple times without failing, doing the actual dispose in a protected virtual method, so if your class is derived, then the child class can also dispose of its resources, and only using a finalizer if your class has unmanaged resources. Finalizers are expensive, so you should only use them if they're needed, and in your public dispose method, call suppress finalize on the garbage collector so it knows this instance doesn't need to be finalized and it doesn't need special management. In the next module, we'll revisit the demo word counter application, looking at what happens if you don't dispose and applying all of our best practices to fix the problems.